So if you have any questions, use your microphone and always use the chat option as well. Although I don't know if I'll see the question on time, so there might be a slight delay with the answer. But this is again a Q&A session, so theoretically I'm here to answer the questions, but I think it would be actually a bit more useful if I go through the brief so that you have all the details, and of course hopefully you see all the kind of all the tricky points, but all the things you need to pay attention to. Okay. So at this point, I hope you have, you have looked at the lecture, the recording from last week. You have found the brief on Canvas under assignments. You've seen that there's some additional documents there. You've gone through the brief as well. So the aim of the coursework here is to design a column. We have the floor layout, the plan of one of the floors, and you have the elevation of one of the frames. So really what we'll be looking at is this frame in the middle. You see here that you have nice rectangular slabs or panels of the slab. And when we look at the elevation, we see that we have two columns with two different lengths. So you'll either be designing this column or this column. And the dimensions will depend on your K number. So in this coursework, if your KU number is 1, 2, 3, 4, 5, 6, 7, and so on, this is your N1, this is your N3, this is N7. Okay, so the different N values depend actually on the corresponding digit of your KU number. Okay, I think this is very straightforward. So you'll have slightly different distance between the axes, let's say CD and DE. You all have slightly different distance. Okay. You have a slightly different distance in perpendicular direction as well. So something between 5.5 and 6.5 meters, and 7.5, 8.5 meters for the distance between axes 1 and 2. So technically these two distances. For the column, you have the column between level 1 and 2. The length of this column will be between 3 and 4 meters, depending on your N6. And for the bottom column, it will be between 4 and 5 meters, depending on your N5. Okay. So theoretically, you'll have different initial data, different initial dimensions. So you'll have unique solutions. Okay. So we'll see, I think, on the next page which one, which was the criteria for level 1 to level 2 and ground floor to level 1. It depends on your KU number. Okay, so I think as far as this part, this page of the brief is concerned, things are very straightforward. Yeah. So we'll assume that these slabs are one-way slabs. We don't have indication that we have a beam anyway, so these are very rectangular panels. The ratio here will be greater than 2, so it is a one-way slab, and we'll probably work with at least with the minimum thickness of the slab of 150 mil. Okay, so okay. This is the assessment page. So when I give you feedback, I'll use this format. But let's get to that point. So this year we're designing a hospital. Okay, this is important because this will help us with the calculation of the loads. So if your N4 is an even number, then you're designing the column from the ground floor to level 1, G to 1. And if your N4 is an odd number, then you're doing level 1 to 2. Okay. We are designing the column in the middle. Okay, so we're looking at axis 2. So this is for the odd. No, sorry, that's for the even. Yeah, that's for the even, that's for the odd. All right. There is a publication, the Good Concrete Guide 9. It's an example of the same building. They're designing typical elements, starting from slab. I think they have beam, they have column, they have foundation. So it's a very good document to have. There is a newer version, but I have access to this one at the moment. So feel free, of course, to find or use I think there's a publication from 2017. Never mind. It's by the Concrete Society. We're changing slightly here the source. Usually we go with the Concrete Center, but Concrete Society has good publications as well, of course. So the next bit tells us about the building dimensions. We have technically done this. Here the explanation is slightly different, but the logic is exactly the same. The first digit is your N1, the second digit is N2, and so on and so on. Okay. Here you'll notice that you have to choose your flooring system. And if you looked at the handout, specifically for the coursework, you've probably seen that there are all these different materials, different weights. This is the source of, let's say, ideas that will help you choose the flooring system that's going to work for a hospital. Okay. The flooring system, of course, will go towards our GK, and also because you have the use of the building, that will help you determine your QK as well. Okay. You also have to think about what kind of roof structure you want to introduce. This will affect your column. So we're not going to design it as a normal floor. We're going to take it as a roof structure. So it will be interesting to see how you calculate the loads from the roof as well. All right, so you have 7 pages in which to fit your calculations and your design and your drawing. I think 7 pages is perfectly fine. Maybe you have actually a little bit spare pages to go. This is because I think you maximum need 3 pages for the analysis. When I talk about analysis, of course, I expect you to do manual calculations, most likely using the moment distribution method. Moment distribution method should not take you more than a page for each item, for the axial load and for the bending moment. It's just if it takes you longer than that, you just need to, if it takes more space, you just need to just get to the key elements of the analysis and present those. Okay, I don't need to see 3 pages of the calculation of fixed end moments. This could be done on 2-3 lines. Get to the table, find your balance moments, find your sagging moments. If you're designing, you actually don't need to go in that detail because you're not designing the beam. And then plot the diagram. Okay, so that's 1 page, another page for the second item for the bending moment in the column. That's 2 pages. First page is initial information. So you have 4 pages left, and you don't really need to have 3 pages to design the column. This could be done on a page or even half a page, 1 page for the drawing. So I think this is more than enough as space, okay? For the assessment, we have here, okay, part 1, which is the analysis. I know that you've learned how to use Superstress, and I'm sure some of you know other software as well. Unfortunately, I'd like it to do a manual calculation, or to use a method that you know, most likely moment distribution, because you can use software anytime. I mean, when you start working, and this is probably what you'll be using for the majority of your working life. But you still need to have an idea about what the diagrams look like and how we get to the calculation of the hogging moment, the sagging moment, and so on. So I'd like to see your calculations handwritten as well, so that you show me that you understand the principles of analysis. And then after that, of course, you'll be using more advanced methods, analyzing very indeterminate structures. But just remember that the output from a computer depends on the input, and the program will not check if the results make sense. So by doing manual calculations, you kind of just get to a point where you can say, well, this is what it should look like. That's what I get as output from the software. So it's either working or it's not. Okay, so you can always go back and change the way you apply the load and correct the bending moment diagram, for example. But this only works if you have an idea about what the diagram should look like. So item number 2, design the middle column for an axial load and bending moments. Well, we do have a lecture on the design of reinforced concrete columns. So you see the procedure is actually very straightforward there as well. Spend a bit of time on the moments. You see that when we are talking about the, let's say, the bending moment diagram, this way, or you can have a diagram like that as well. We start with some values from the diagram, from the analysis, but we also have to consider some eccentricity of the applied axial load. So technically, we'll have a small addition here, which is technically EI and ED. Okay, so this moment, okay, which is the greater of the two, will be our MO2. Then for the bottom, you see that we have a slight reduction of this moment. And when we calculate our C value, you remember that we have 1.7 minus Rm. So for the calculation of this Rm, we're technically looking at the ratio of the two moments. So one is, how to say, we overestimate it, the other is underestimated. So we're technically saying, okay, we have eccentricity, this could add to the greater of the two moments, and by that logic it will reduce the other one, because this moment E times N, your eccentricity times the axial load, will kind of give you, let's say, tension on the left-hand side of the column or on the right-hand side of the column. So it's a constant moment from top to bottom. And what makes things more interesting is that we have a value for Rm, which is usually less than 1. So if Rm is less than 1, technically here it's negative 1. So you have minus 0 0.9, minus 0 0.8. Your C value will be greater than 1.7, okay, but it will be less than 2.7 as well. So when we calculate our lambda limiting, okay, where you have ABC square root of n, if your C value is closer to 1.7, okay, technically we are calculating the more conservative value of lambda limiting. So we are, I'd say, being kind of looking at the worst case scenario for our column. And of course, lambda limiting will be the criterion for the classification of the column. So if lambda limiting, for example, is 30 and our lambda is 25, then of course we'll have a stocky column. Okay, but if it so happens that lambda is 32, then we'll have a slender column. Now, I want you to design your columns as stocky. So we haven't talked about the sizing of the column in this presentation. I've talked about preliminary sizing in the lecture on columns. But if you look at the good guide, I think they start with 300 by 300 for the level 1 to 2 column. Possibly for the bottom column, I would expect you to go with 350 by 350. Okay, so these are the dimensions that should work. So 1 to 2. Or they might not exactly work because you'll have different lengths, different loads. So it will be interesting to see how you design your column. Okay, so 350 actually millimeters. Okay, so this is ground floor to level 1. If 350 by 350 doesn't work, probably 400 by 400 should be fine, but don't start with a very very big cross section, because remember we're aiming for economy of the material, obviously. What kind of concrete? C30 minimum, C40 for the bottom column if you have to, but I think C30, 35 should be okay. Okay, so this is item number 2. I didn't talk about the axial load actually, but if you go through the lecture from last week, teaching week 17, I think you'll get a very good idea about the calculation of the axial load. But I'll come back to this after I finish with the assessment criteria. Okay, So item number 3 is a drawing of the reinforcement. Okay, so I want to see an elevation of the column. So I see where the bars are supposed to go. What's the distance between the links? Okay, what's the connection to the bottom and the top elements? If you have a ground floor to first level, first floor column, that means connection to the foundation. Okay, and of course to the beams, the first floor, the first level. Some probably you have some bars sticking out because you need to have continuation of the reinforcement. You'll remember that you have, let's do a bit of a quick drawing. So you will have some foundation, okay? You will have some starter bars. You have your column, not a very good drawing. You have your beam and slab, so you have your bars, okay, and you have your S reduced and your normal S, okay. So I want to see something like that. I want to see a cross section, of course, top or bottom. So I want to see where the bar should go. I also want to see the detail of the link, okay, because remember we have the concrete under compression, so it will try to expand a little bit in lateral direction. What we do with the links is we confine it. We stop it from exploding in. It's not going to explode, of course. Just deforming in lateral direction. Okay. So I think this is okay for the other level. Of course, we have the bars coming from the previous level. We have our bars. We have the links again. Okay, this is just to indicate that you have S and S reduced. Again, cross section. And of course, you need to give some detail here about what kind of bars you're using, the dimensions of the column, perhaps the D2 value. Okay, so these are the standard standard things which will just show your design. By the way, sometimes you for some reason you go into kind of doing your drawing using only half the page. I don't see why you can't do the orientation like that, just to give a bit more detail. Just utilize the space. All right, so that's about the drawing. I think we have one more item here. If I can find the menu. Right. Okay. The last thing, and you'll notice here that it's 20 marks, so that's the difference between the A and B for some reason. It's the difference because I don't know, sometimes you don't go through the whole sheet, through the whole page, and you don't bother doing some of the things I ask you to do, and then you don't get the full marks. And why didn't I get full marks? The last bit is your kind of interpretation of the problem, your solution. So the client of the building would like you to convert the roof into a terrace. So here you have to explain how would that affect your structure and specifically your column. So possibly you'll be looking at some typical solutions for the floor. Would that increase the weight on the roof? Okay, so floor, then roof weight, well, usually does. Okay, and then how does this affect your column? So if you assume that you had a reaction of 300 kilonewtons from the roof, but now it's 500, do you have spare capacity? Is the column going to fail if you add 100 to 200 kilonewtons to the column? So it's really your interpretation of this problem. I wouldn't go with more than, let's say, half a page. Yeah, I think that should be all right. It's meant to kind of to challenge you to think a little bit how the initial data can change at some point during the design, and how you have to update your design, how you need to update your models, because this happens, of course. Okay, so I think if you have a proper analysis, you get 30 marks. Don't forget any units. Make sure there's enough information for me to understand the steps of the analysis. If you design the middle column and you do all the steps correctly, and you have the the correct RM and the correct C, or the conservative C, hopefully you're going to get 25 marks. If you so find that you have a slender column, go back, increase the dimensions of the column, and design it as stocky. Nothing wrong with a slender column, I have to say. It's just the procedure is slightly more complicated. We need to determine the moments, the maximum moments on the left and on the right of the column, so that we can obtain the worst case scenario, the combined bending moment diagram from the first order moments and the second order moments. And it's the second order moments, they take a little bit of time to determine. However, we haven't really looked at the design of slender elements, so I would prefer if you go with stocky, especially if you have a bottom column which is longer, subjected to the great moments. It's just more conservative to design your column as stocky. But that's, of course, unless the architect is happy to accept some changes in the design of the elements. But in this case, we have a very flexible architect, so they'll accept your suggestions. If you have a nice drawing where you have information about the longitudinal bars, the links, you have the right detail of the link, you have all the required information. Again, there are a lot of examples, or enough examples, in the lecture from Teaching Week 17. You should get 25 marks. Okay. And then if you have a logical solution to the problem, where the client is called the client, by the way, you can, I guess you can, no, just dear client. So you can write him or her a letter and explain what will happen. Have a logical, then 20 marks, and this should give you 100 marks. Of course, some people will make mistakes here and there, so I don't expect everyone to get full marks. But if you spend enough time on this course, actually, it is very easy to get the best result. Okay, now let's have a look at the handout, because this is where we have we have information about the loads. And just check very quickly if there are any questions. Okay. Good luck with the presentations. Okay, where are we? Okay. So in the handouts, you have typical loads from different materials. Okay. So for example, here you have the unit weight for screed. You have loads for from brickwork, let's say concrete plane, 24 kilonewtons per cubic meter, but they haven't included the reinforcement. So for reinforcement, we're going to add 1 kilonewton per cubic meter. We have some precast hollow core units. That's interesting. Waffle slab. Um, we have raised floor. Okay. Again, some screed. These are now area loads, so they are expressed in kilonewton per square meter. Okay, and then we go to table 215. What do we have? We have cavity wall, we have cladding, precast concrete cladding. We don't have a perimeter beam or a column, so we're not going to worry about the cladding, but just it's good to be aware that those beams do carry the load from the cladding as well. We have typical office floor. Uh, this is on the use of our building. It's not a residential building, it's not a school, but it is a hospital. So here, technically, what we have is a system that you can use. So some sort of flooring system. We have then the weight of the slab. We have screed on top of the slab. So probably something like 50 millimeters. Suspended ceiling, some services. So you're looking at permanent load as area load in the region of about 8-9 kilonewtons per square meter. Here, by the way, the assumption is that the slab is 250. So it will depend, of course, on your choice of depth of the slab. If you're going with 150, obviously this area load 625 will be an overestimation of your GK. Okay. We also have here flat roof and external terrace. Okay. So you can have paving, you can have, or you should have waterproofing because this is the roof, thermal insulation so you don't get heat losses through the roof. Slab, suspended ceiling, services. So you see here that the services are 0.3 and on the top there is 0.05. Probably it's better to overestimate the services a little bit just to be on the safe side. At the hospital, I guess you have all kinds of services running through the building. Timber pitched roof probably not going to be the best option for your structure, but if your initial solution is that this would work for these pans, probably not. If it's justified, I'll accept it, but still reinforced concrete, flat slab, flat roof, most likely. Okay. Then we move on to the variable loads. Table 2.1. So in order to know which table to go to, you need to know the category. So we're looking at A, B, C, D, and so on. I believe we are either in A or B. Let's see. So this is domestic and residential. Doesn't sound like us. We don't have, it's not communal, it's not bedrooms, it's not snooker rooms, not balconies. Okay. Oh, next year I'll make this a hostel. See what is gonna, how is this going to affect the load? It's not offices. Let's see, areas of congregation, areas with tables. You could have some cafes and restaurants, but we're not gonna go in that detail. Areas with fixed seating. It's not a place of worship, although of course you can have it. So I guess this is still not our table. Shopping areas. All right. And at some point we will come across a hospital load, but it seems that this morning I have skipped it. Okay. For the variable load, it will be between 2 and 5, really. It is somewhere in these tables. So it shouldn't be too much of a problem to find it. Just go, read them carefully. Most likely areas of congregation. No. Okay. Okay. And worst case scenario, you can always take your variable load as 2.5 and work with that. Okay. The good thing is you do have the handout, so you will you can pick the loads not only for this but also for your designs, for your group projects, because I believe that you're probably now thinking about your conceptual designs and your final designs. Okay. By the way, for the roof, we're not designing it for a helicopter because we'll assume that the helicopter can land very close to the hospital, and we don't have to add this load on to our calculations. Okay, so the steps of the analysis, as I see them, will be the choice of the flooring system. So you'll probably have a screed, you have some flooring system on top, you have your slab, you have some suspended ceiling, okay, you have some services, cables and things. So you will have your area loading from this flooring system, and essentially what you have is a series of frames, okay, and of course you have a slab, so you have your beams, okay, and you have some columns here supporting your continuous beams. Obviously these columns are longer than that. Okay, and you have columns. You have columns this way, this way, this way. You have some columns there, there, and there. So essentially what we're saying is that from this part of the slab, we'll have we'll have this area contributing to our beam. So if you have the GK and the QK as area load, okay, obviously you'll be able to determine the 1.35 GK, 1.5 QK to find your design load. And when you have the design load, you can then use the width of this portion of the slab, W, and this W is technically this distance here, okay, because it's half of the span to the left and to the right. The spans are equal lengths, so by multiplying this with W, you obtain your UDL. And this is the UDL that you're going to use to analyze your beam as a continuous beam. Okay. Now, we're not going to worry too much about the envelopes here. We're going to put full load in the left span, full load in the right span. what we need to know is really what our diagram would look like, okay, in terms of values, okay. And most importantly, we will have, of course, some shearing forces as well. So technically, we need to find our reaction at this support here, which is the reaction from the analysis of the left span and the right span. So we're looking at the reaction RB. This will be our axial load for the column. Now, of course, at this point, you can say, well, can I use a different type of subframe? And the answer is yes, of course. However, because it has 3 joints to analyze, I think students are put off a little bit, but just be aware that this is the actual subframe that we usually analyze to find our moments in the beam and in the column elements as well, and shearing forces as well. So you have the option to do this. I'm discussing this in the lecture from last week. But if you want a slightly quicker analysis, the continuous beam with 2 spans is probably the safer option, the easier option. Okay, of course, we have the continuous beam to find the reaction in our column, to find the axial load in our column. We also need to determine the moments in the column. So for that, we can use a subframe, okay, that will take that portion of the frame. I'm talking about really this subframe here, okay, or the one above. Here, what we'll usually do is we'll put the permanent load, the variable load, and on the other side only the permanent load, with the idea that we'll get some rotation of this joint. So we'll have a moment there that has to be balanced by the columns above and below the level, the floor level. So if we have both permanent and variable load on both sides, we'll see that the difference there is very small. So we can just keep the variable load in one of the spans, usually the longer span. And to make things even worse, you can use a coefficient of 1 for the permanent load in the right span, so you get a greater moment in the middle. So the idea is that from this analysis, you get a diagram, bending moment diagram, that will give you tension on the top and on the bottom, on the different sides of the beam, so left and right. So you get this kind of diagram. Could be, of course, mirror image. It depends on your moments. So this will then give you your M1 and M2, and you can then proceed with the design of the column. Now, if you look at the good guide, they have analyzed the full frame, and for the bottom column, they have assumed that the bottom connection does not kind of resist the rotation of the column. So for the ground floor to first floor, I'll actually probably expect to see the bottom connection to be a pin. So instead of having this, you're going to have a pin connection. Here, the connection really depends on what kind of foundation you're going to have. Is it going to be stiff enough to resist the bending, the rotation of that joint? I think in the good guide today, they have slightly poor soil conditions. poor soil properties. So that and the fact that they have a pad foundation, I think could give us the justification to assume that we have a pin. In reality, it's most likely going to be something between a pin and a fixed support. But let's be a bit conservative and go with the pin. Okay, for the ground floor to the first floor. Let's use this assumption so that again you have two different solutions or two different setups for the location of the column, for really the uniqueness of your solutions. If that's the case, though, so you'll have a diagram that will have only M2. Okay, so this diagram obviously will be slightly different. Okay, for your group design, because you're probably going to have a pile foundation or you're going to have much stiffer foundation, the fixed support probably is fine. Okay, right. So I think in terms of information about this coursework, I've covered more or less what you need to know. Go through the recordings, of course. Here, you need the T-beam, so you understand how to calculate the loads on the beam. Okay. You need the reinforced concrete column presentation, because you need to know the procedure of the design of the column. Okay, so there's a handout as well. In terms of steps, it's really calculating your slenderness, calculating the limiting slenderness, finding the classification of your column or the category, stocky, slender, stocky really, and then using the M and N and the corresponding charts, 9A, B, C, D, and E. You then will calculate the required area of the reinforcement. If it so happens that you don't have a value for the AS, then what you'll do is you add the minimum percentage of the reinforcement. This could happen because in this analysis we see that the moments are relatively small, but then again you might have quite an interesting reactions, so quite an interesting load in your columns. About the actual NED, because of course you remember that each column carries the load from the column above, you have to add those loads as well. So you will have reaction from the roof, you will have the reaction from level 3, so or R for the roof, have the reaction from level 3, and you have the reaction from level 2. This all goes into the column between levels 1 and 2. And for the bottom column, you also have the reaction from level 1. So obviously level 1, 2, and 3 are the same, so you can multiply that reaction by 3. And from the roof, you're probably going to have slightly different value. It all depends on what kind of roof structure you go with. And this will give you the value of your axial load of your N. Okay, so I would, as usual, recommend to go through all the lectures. Okay, again, T-beam, then RC column, then of course the RC tutorial. Okay, this in the RC tutorial, I'm talking about the analysis of the analysis of the subframes. I'm talking about the details, the drawings. So the part about the columns will be, of course, most relevant. But of course, these lectures will also help you design two elements, a beam, T-beam, and the column. And I believe you have 4 items that you need to design. So automatically you have now 2 things that you can design if you're doing a reinforced concrete structure. Next week we're going to talk about slabs again. We did design one-way and two-way slabs last year, so you have the notes from that. You also can design the slab, okay, if you have a solid slab, and then you have to think of a 4th element that you need to design. Usually that's the foundation. Okay, so I think I've covered more or less everything we need. Let's see if there are any questions. If there are any people left. Yeah, so in the drawing it says 150. 250 is just the example they have in the handout. Okay, so start with 150. It could go to 160, 170, 180, 190, 200. But 250 probably will be over estimation. The spans are between 4 and 5 meters. It shouldn't really give you a very deep slab, but if you want to do some analysis on that, that is fine as well. Okay, as long as you fit in the 7 pages. Are there any questions, other questions that you would like to discuss? I know that you did your steel coursework using using Excel. Sometimes students do use the same file and submit more or less the same coursework. So from this point of view, I'd prefer if you submit a handwritten document. Feel free to use the frame because you have the template, you have the setup for the from the steel coursework. But I myself want to see that you have at least written the part yourselves. This is just a bit of a plagiarism prevention. Okay, I know that it's much easier to set up an Excel file and use it for any other designs. That actually doesn't mean that you can't do it. It's just you have to present your work like I said. Okay. So I think now you have probably about 3 weeks to work on this. Next week we're going to have a lecture on slabs again. So I assume that after we talk about the rib slabs and the waffle slabs, we can spend a few minutes on the coursework as well. But to be honest, you do have the all the information for the coursework online, as in on Canvas. So it's just a question of going through the lectures. What do you mean unlock the analysis video? Is it from the teaching week 17? Do you mean the lecture or do you mean the tutorial from teaching week 17? Okay. I wasn't aware that there should be a a video that will, there should be a link that takes you to Box. Can you find the link that gets you to Box? Both, so I update the schedule and the reinforced concrete from the home page. There should be two links. One is the streams, which I'll check. I don't know why it's locked. And the other one is the recording on Box, because I download the videos usually. Okay, I'll check. All right. Anything else? Does anybody have any problems with the PDFs? They are they're not new in terms of, they're not a version that okay. Let me check what's happening. Okay. All right. All right. Need the, let's say 66B. Okay, so when we go to assignments and RC coursework, I can view them, I believe. Okay, and should be also able to download them. Yeah, it's downloading. Let's see with the handout there as well. So I can download it. Yeah, it's downloading, as you can see on the bottom. Let's try the other module, because we have thousands of modules here. Occurrence A. Okay, it's downloading again. So I don't understand why it's not, you don't have access to it. What I can do is I can put these files on Box and put the link under schedule. Would that work? Okay. Okay. So what I'll do is I'll go on Box and just put the link. So you're looking for the link under assignments, I guess, and schedule, so that you know where to find it. Okay. I think I can stop with the recording. Stop.